Data structure using C++, Module 5, Session 6. In the previous session, we had discussed what is a binary search tree. To recollect it back, a binary search tree, in binary search tree, one rule which you need to follow, the most essential rule, ensures that you have to make sure that the node is having a value higher than that of its left child, and it is having a value lower than that of its right child. So now also we have address, so this binary search tree where it would be useful. So it will be helpful provided you use in order traversal technique to sort a given key elements ascending according to ascending order. If you want to arrange the key elements according to ascending order, then you can invoke the method. The traversal method needs to be used. The traversal methods selected over here would be in order traversal method, and based on that the key elements will be displayed. If at all, if it's a binary search tree, all elements will be displayed according to the ascending order. So now we will look at some of the methods which needs to be uh, addressed. So first method is how do you find whether the key element is existing in the binary search tree or not. That's the first method, and we will discuss, or we will call it as such. And the two more methods are nothing but the insert and the delete method. So insert method is to ensure that you have to first find out whether the key element is present in the node. If it's present, then at that position, the pair, since you are inserting a pair here, this is meant for dictionaries, you're inserting a pair, the value has to be replaced, the previous value has to be updated using the recent value. Similarly, if you are deleting a node, first check whether that particular key is existing in the binary search tree. If it's available, then you have to delete the complete binary search tree. Okay, and also one more method where you find binary search tree helpful would be for arranging the keys according to ascending order. So first we have to understand what will be the node form, the characteristics of the binary search tree node, how it will look like. So we will discuss this, how exactly pictorially it will look like in a while. So it will be having actually the node would have four components. Two, we call it as element, and element field is splitted into two, which is element dot first and element dot second. So element dot first field has carries the key, and element dot second field carries the value associated with it. Along with this, the node will also have left child and right child, so two pointers, one structure which has been splitted into element first and element second. So if you're not familiar with this, you can go back to module 3, have a look at the dictionaries, wherein the node format of the dictionary is addressed, so you can figure out that. So if you're confused with this node tree. Okay, so the method adapted for arranging the keys according to ascending order, one line code. So how this works, we will talk about it. So first, binary search tree, you have to derive it from linked binary tree. This linked binary tree happens to be the class which we have seen when we were discussing module 4. So I'll just move back to that slide. This is your linked binary tree class. So this had many methods. This was the last topic which was discussed. And here you can see there is a method known as preorder output. Similarly, in order output should be there, and level order output, also post order output. So since in order output is not existing here, you have to insert that line. Since the code size would have, I thought it would have increased, that's why I'm not included it. But in here what we are trying to do is this whole class has to be made visible to this function, this binary search tree. Okay, binary search tree is derived from linked binary tree. In that case, all the components, whatever you have here, will be in accessed by this binary search tree. Okay, and here the main method which we are calling is the preorder output sequence. So preorder output sequence is used for printing the elements in preorder manner. Along with that, here we will call the method ascend. Okay, so first ascend method, what ascend method has to do is it has to print the element according to ascending order. So if we figure out that if the binary search tree is the input which is taken by this in order output function, definitely it is going to display the element according to ascending order. We have already seen this because binary search tree, the condition is the node value, node element will be having a value higher than that of its left child, and it will be having a value lower than that of its right side. So suppose if the binary search tree contains three elements, namely 10, 20 and 30. 10 would be the left child of the node 20, and 30 you can consider it as a right child of the node with value 20. So if you approach in order output sequence, so in order form traversal technique, we visit the left child first, followed by the root, and followed by the right child. So if we move according to this first fashion, you'll be getting the elements arranged according to ascending order. Now we consider that the key is integer data type now. So it could be any data type. So k is one of the data type, e is another data type. So for understanding it in a better way, we always consider k as integer and e would be a string. So this is a word, literally this is its meaning for a dictionary. Okay, so hope this made sense. So just remember this function void ascend call in order output. Probably in the exam point of view, you may have to elaborate what is in order output function. So in order output function, you may have to write first here void in order output, then that calls recursively in order of output. Okay, and again pre-order or in order function, we search whether it is root, then we will traverse it is there here. This is the program, again a small program. So in place of pre-order you have in order, and it's not something like you visit the node first. So first left child, then visit, then right child. So hope you may have to write this also in case if it's asked in the exam. Okay, okay, the next concept, let's discuss the methods, important methods: search, insert and delete for binary search tree. Search implies searching whether the key is existing in the binary search tree or not. So to understand the search method, how it works, so to search for a key, first what we need to do is we need to begin from the root. Suppose if the root is null, then you don't have that element, so your search returns unsuccessful. Suppose if the key is present, um, it suppose if the binary search tree is not empty. If it's empty, then it returns null, saying that a key found is unsuccessful. If it's not empty, then definitely you have elements. And how the search will work, so first we compare the root node with the key element, the key which we are supposed to search for. Suppose if the root element is greater, then the region to search would be only on the right tree. Go to the right subtree, and that's your region where the search needs to advance. If not if not it would be a left subtree. Okay, similarly, if the key in a key value, if it's greater than the root value, then you are supposed to move on to the left subtree. Okay, the key value, if it's lower, sorry, if the key value is lower than the root, then left subtree is actually the region from where you need to search. So basically this is bit better technique to search for an element in a given array or a list, because a total number of iterations which we need to carry out for searching an element would be lower. Fine. Now let's discuss the program. Before beginning with the program, let's discuss the node form here. So here, this is your node, this is a node, and this is having four elements, two pointers addressed as left child, right child, because it has to point to some other nodes of this form. And this node has a pair which we call it as a key, and this is the key value, k value, and this is the e value. Just to ensure that the size of the node doesn't grow, I've taken this as a small number. Key is a small number here, and the word is two digit or two character word, so it could be a huge word also. Literally we will be storing here the word meaning. If this is the word, its meaning we will store. To understand in a better way, rather than taking a word, we take it this as an integer number. So this is the key element. This is the key which we will be searching whether it is available in this tree. Okay, so I repeat, you have one struct. This you can call it as a struct, which is element. Okay, and element has two fields. Element dot first is this 50 and element dot second is w1. Okay, and along with that you have two pointers, left and right. So this is the structure of your binary search, a binary tree node pointer. So binary tree node pointer, whenever you're creating, it is not something it is having one value. Element is having two field. Earlier we had taken element with one field, if I'm not wrong, when we are working with a max tree or a binary tree. Okay, now let's discuss this program. So here we define template class k and e. So what is k? K is the data type of your key, and e is the data type of your word, meaning value for the key. It's a data type. So in this case it is string, k is integer. Now the first command which we are using, pair. So it is a pair pointer, binary search tree. So we have seen what is this pair pointer, pointer to the pair of node, and this has two fields, ke, and it is a literally a node which is having a left child as well as a right child. Okay, so now first what we need to do is, this is actually the method which we will be picking from binary search tree. Remember, find is a method from binary search tree. It takes the argument the key value. Okay, and here the first job that we need to do, we need to check whether do you have elements present in the binary search tree. If it's not there, then we have to return null. If not, if it's not empty, then we have to look which is actually the region, or which is the area where we need to search for this key element. So first condition as addressed in this algorithm, first check the root, compare the root with the key value. So since it's having value, then depending on the value of the key value, if it's greater than the root value, then the search area will be right subtree. If not, it would be left subtree, and you have to recursively proceed in the same manner till you search whether the element is present or not. If it's not there, then you will be returning nulls, indicating that no match exists. Okay, now so just understand. So first we create binary tree node. Remember, binary tree node class, we have the structure we are familiar with, but it included int or character. It was t. Right now this is pair with the two key elements k and e. Now this is one difference because of which this structure I have addressed. Okay, and the p is a pointer which is pointing to the root. Okay, so this is the structure. Now this is the root, and p is also a pointer which is pointing to the root. Now this is your root, this is its left subtree, its left subtree is this, and this way it follows. So when you look at this tree, it is a binary search tree wherein every element, root element, is having a value greater than that of left child but lower than that of right child. Now let's assume that the key value which we are searching for is 20. We need to figure out whether 20 is there in this binary search tree. If it's available, then the whole this is actually your element structure with the two fields, key and value. So this whole structure has to be returned back if it's agreeing with the key value. Okay, now let's go back to the program. The key value is 20, and when we observe the structure, 20 is already existing here. So what we do is 20 will be compared with 50, and since 20 is lower than 50, we have to change the pointer position. P, if it was pointing here, make the pointer point to this node. Okay, then again compare the element present at this node, which is 40. Compare 40 with 20. Again we find out that 20 is lower than 40, so again you have to traverse to the left. So again change the pointer. P will be its left child, so here it will point. Then again 25 will be compared with 20. Now when this is the case, again we find 20 is lower than 25, then again we have to traverse towards its left child. So here finally the pointer will be. So when this is the case, now we find whether it is less, it is not less, then we will check the another condition, is it greater. Even if that's not the same, then definitely it should be equal. So if it's equal, then we will return this whole object, that is 20 and w8 both together will be returned back from this program. Okay, because it is going to return the pair. The pair is the return type. Okay, now let's see. First, P is pointing to the node, so here it points, that's correct. Then we will check uh, while P not null. Now the P is not null because this has element present. We have to examine the element. So since it is a pointer, to get the element value from this node, we will be using arrow mark. So first, the key value is 20. We check whether the key, which is 20, is it less than P element dot first. Now element as address, this is the complete element structure with the two information, first and second. So element dot first value is 50. So 50 is compared with 20. So we come to a conclusion that 20 is less than 50. 20 is less than 50, so you have to change the pointer which was pointing to the root. Now it has to point to its left child. So if that, then the case would be P was pointing here, now P gets pointed to here. The left child of the root is this, so here the P points to, so P is changed. So P is changed, so it means this is your area, this is your region to search. Now the next, we go back here again, the while loop is continued because P is not null. So since it is not null, again we examine this, the key element, is it less than P element dot first. So P element dot first, now you are in this node, so P element dot first value is 40. So 40 is compared with 20, 20 is less than 40. So again we have to change pointer. P should be made as P of left child, so P should be pointing here. Now the P will point here, that is when this because this condition is true. After that again you check while P not equal to null. Now the scenario, this is actually the node P where it points to. Here the value is 25 and the key value is 20. So again 25 will be compared with 20. So so 20 is less than 25. So again we need to traverse here. We have to go to P of P left child. So pointer finally it will point here. So this will be the P position. It points here. Now let's see what happens. So in this case, when you look at this has an element because the element this at this node it is 20. So we check this if the key is less than element dot first. Element dot first is 20. The key is 20. So both are matching. So this is false. Then we check this condition. Else if the key is greater than element dot first. Again we figure out it is equal to condition. So this will also be not true. So the finally it is going to equal to condition, which means return the complete element. Return the complete element belonging to the pointer. P element whole structure is returned back, and the structure has two components, that is W8 and 20. So you have an element, which you are going to search. It is existing and its position is W8. So whole thing will be returned. Now when you examine how long it will take to search for an element, since you are having 8 number of elements here, total number of elements or key elements present in this binary search tree is 8. So the iteration was, first iteration the pointer went here, second iteration it went here, third iteration it went here. So 3 iteration is fair enough to figure out whether the element is existing in the binary search tree. So otherwise if you are following linear search, you may have to search. There might be a worst case scenario, 8 iteration you may have to go through. For 8 comparison is required to check whether the key is present or not, which means here total number of iteration is given by the formula log n to the power base 2. If n happens to be the number of elements, you have log 8 to the power base 2, which is 3 in this case. So at max 3 iterations. Okay, so this is bit effective method because elements could be searched in an effective manner. Now suppose if the element is not found, then this whole program is going to return null, indicating that there is no key present. So if you can take, assume you can take 75 as the key element. So initially P will point here, then 75 is not less, it is greater. So in that case you have to go to P will be P of right side. So you will point here. Again 60 will be compared with 75. 75 is greater. Again you have to traverse to the right side. So here you will be, again you will compare P of left child with the the element, the right child value is 65 and the element is 75, 75 is greater. So again you will go to the right child. Now when you are visiting the right child of this node, it is blank, it is null. So we return null, saying that it is going to return null, saying that you don't have an element. So that's how the program works. So the program works. So I think, if I'm not wrong, the return null, this command should go here. If I'm not wrong, I don't know. We'll see. We'll see that. So here I think it should be finally return null. Okay. So this is the program for finding the search. The other two programs, insert and delete, we will look at the next class. We will discuss this.